Hello guys, today we are going to learn about a little bit about network traffic and let's go into it. I will go through every step here and at the end we're gonna take practical example. So here we go. What we got? Network traffic analysis, NTA, is a process that encompasses capturing, inspecting, and analyzing data as it flows in a network. Just like this. That's it. That we need to remember right now. And we should why should we analyze network traffic? Before we answer this question, let's take a look at the following scenario. DNS tunneling and beaconing. So those are the two ways that the DNS can be modified. You are a SOC analyst and you receive an alert stating that an unusual number of DNS queries are coming from host Win016. And those are the logs on the firewall. So we can, based on that, on those DNS logs, we can retrieve the following information: query and query type. So what kind of commands were used, subdomain and top-level domain. We can check tools like AbuseDB or VirusTotal to check if domain is malicious. And this host IP, we can identify the system sending out the DNS queries. Destination IP, so we can actually track everything here. If we spot something that in DNS is out of place, and this timestamp, so when it was done. The DNS logs don't contain more information than that, so it's hard to draw a conclusion based on that information alone. And there is another scenario why we need a traffic analysis, and they say firewalls and other devices register DNS queries and the responses, but not their content. Threat actors could, for example, use TXT records to send command and control instructions. So they can manipulate the data to send command and control instructions. We can discover this by inspecting the content of the DNS queries. The packet capture fragment below shows that the content of DNS reply that contains C2 commands. Okay, probably those are those queries, CMD1, CMD1. Yeah, this is the central command and control instructions. Why should we analyze network traffic? Just in short, monitor network performance, check for abnormalities in the network, inspect the content of suspicious community internally and externally. Exfiltration via DNS, download of malicious zip file over HTTP, lateral movement. From a SOC perspective, network traffic analysis helps detecting suspicious or malicious activity, reconstructing attacks during incident response, verifying and validating alerts. Below are the two more scenarios that illustrate the importance of network traffic analysis. Based on the logs for end-user system, the system began to deviate from its normal behavior around 4 p.m. Analyzing the network traffic going to and from the system, we found a suspicious HTTP request and were able to extract a suspicious zip file. So there was zip file when they analyzed the traffic network going to and from this system, and we received an alert that an end user system is sending many DNS requests. So when an end user system is sending many DNS requests, they are about to do something. After inspecting the DNS requests, we discovered that it was being exfiltrated using a technique called DNS tunneling. So DNS tunneling, it's like modifying the DNS queries in a text form. So now that we know why we need traffic analysis, let's continue with the next task to discover what exactly we can monitor. What is the name of the technique used to smuggle C2 commands via DNS? So they basically speaking about those two techniques, tunneling and beaconing. But in C2 commands, so control and command commands, they are the DNS tunneling, because the data was being exfiltrated. DNS tunneling. Okay, now there is a more about network, the network layers that many in cybersecurity have to remember that and learn this. The best way to showcase the traffic we can observe in the network is by using the architecture implemented in nearly every device with a network interface, TCP/IP stack. The image below shows the different layers of TCP/IP model. Each layer describes the required information to pass the data to the next layer. Okay, so we got here application plus data, application layer, transport header, transport, plus application header plus data, IP header, transport header, application header plus data, and link layer, transport IP header, link header. On the application layer we can find two important information structures, the application header information and the application data itself payload. This information will change depending on which application layer protocol is used. Let's look at an example of HTTP. So this is HTTP protocol. The code snippets below show the application header of client sending a GET request and server response. Most web proxies as firewalls log this header data. What they don't log is the application data or payload from the GET request. You can determine that the client is requesting a file named suspicious packet zip. The server response includes 200 code, which means the request was accepted. However, what you can't see in the logs is the content of the CIP file. So here we got the get content, download suspicious package zip. So it wants to get this data, get this file. And response is okay, 200. In the transport layer, so this was application layer. Now we got transport layer. And the application data and header are segmented and encapsulated at the transport layer into smaller pieces. Each piece includes a transport header, in most cases TCP or UDP. Let's have a look at the firewall log entries. So what's going on from the firewall? Got sources, this, and destination, port, Firewall logs often include the source and destination ports. However, they are valuable for detecting certain types of attacks, such as session hijacking, session hijacking. The output below shows a series of packets captured with Wireshark. Wireshark also captures all packets from the internet, and we got TCP connections, as you can see, and they explain the first three lines show a normal TCP three-way handshake, so normal connections. Lines 4 and 5 legitimate data transfer. Line 6 shows a packet from another source trying to inject itself into the session. Note the massive jump in the sequence number here. Okay, let's move on. When the transport layer sends down a segment, the internet layer also adds its header. If the segment is larger than the maximum transmission unit MTU, it will be divided into fragments. So in the internet layer, the transport layer sends down a segment. The internet layer also adds its header. If the segment is larger than the maximum transmission unit MTU, it will be divided into fragments, and the header will be added to each of them. So this works really smart. Like if the packets are too large, they can just segment. They can divide. The fields that are most often logged are the source and destination IP and TTL. This is sufficient for most use cases, but if we want to, for example, detect fragmentation attacks, we will need to inspect the fragment offcell and total length field as well, and we do it in the Wireshark. There are different variations of fragmentation attacks. For example, an attacker can create tiny fragments to evade to IDS or mess up the reassemble of fragments by using overlapping byte ranges. Yes, so the attackers can send the packets in the very small fragments and very large numbers. And we got this means that the complete packet can be reassembled one way or another, so it can be assembled. Okay, attackers can use this technique to bypass an IDS, for example. Then we got the link layer. Once the internet layer finishes encapsulation, the IP packet is sent to the link layer. The link layer adds a header as well, containing more addressing information. Most logs will display the source and destination's MAC addresses. Most logs will display the source and destination MAC addresses for certain types of attacks, for example, RP poisoning or spoofing. The information in the logs won't be sufficient. For these types of attacks, we need the full packet and context. What you, for example, can see in a log when the MAC address appears from multiple interfaces or when many gratuitous RP packets are sent out with conflicting MAC addresses. The example below shows a packet capture detailing an RP poisoning attack. The host IP is replying to each RP to request with the same MAC. So this is actually asking who has the 192.168.1 and 10 IP, and to tell the other IP. And this is actually servers or computers communicating with each other. And this is here the attacker's spoof. Okay, let's go to the questions. Look at the HTTP example in a task and answer the following question. What is the size of zip attachment included in the HTTP response? Note down the answer in bytes. So zip file, we need to look for the zip file. Zip file bytes follow. We got 10,485. 10,045 bytes. No. Content length is this. Okay, which attack do attackers use to try to evade an IDS? So wait, what is IDS? IDS stands for Intrusion Detection System. Network IDS monitors traffic flowing through a network. Example, watches packets moving between computers, detects port scan, malware traffic, suspicion of its brute force attacks. Okay, so IDS is the Intrusion Detection System. Which attack does impact the IDS? Let's find it. What is IDS? IDS in the internet layer. There are different variations of fragmentation attack. For example, an attacker can create tiny fragments to evade IDS. So one of the techniques are the fragmentation attack. Let's see. Fragmentation. What field in the TCP header can we use to detect session hijacking? What field in the TCP header we can use to detect session hijacking? TCP header. What do they mean by that? TCP three-way handshake. Yeah, they're talking about here session hijacking can be detected by analyzing the sequence number, including the header, sequence numbers. So what field in TCP header can we use to detect session hijacking? It's the sequence number. That was really unusual here, sequence number. We can detect it when we see this abnormal number. We see that something is going on here, not really good. So this really catches the eye of the cybersecurity analysts. Okay, let's go through another. There's a lot of it, I would say. So in the previous task we discussed that we can observe theoretically based on the TCP IP stack, so network layer. Practically it's more helpful to focus on specific sources and flows. A corporate network typically has some predetermined network flows and sources. We can group the sources into two categories: intermediary endpoint. So endpoint are the computers, intermediary are probably the routers or something, and switches. The flows we can also group into two categories: north-south, traffic that exits or enters the LAN and passes the firewall, so normal traffic; east-west, traffic that stays within the LAN, including LAN that extends to the cloud. Okay. Sources. As mentioned, the two network traffic sources exists: endpoint and intermediary. These devices can be found within the LAN and WAN. Let's just recap what those are. Difference: LAN, local area network, devices in a small area. The LAN connects devices in small area, and WAN, wide area network, connects networks over large geographic distances. Example: the internet, company offices in different countries, bank networks across cities. Okay, so it's wide network. These are devices which traffic mostly passes. While they generate some traffic, it's significantly lower than what endpoint device generate. Under this category, we can find firewalls, switches, web proxies, IDS, IPS, routers, access points, wireless LAN controls. The traffic that originates from devices come from services like routing protocols, management protocols, logging protocols, and other supporting protocols, RPs, SDP, DGSP. Endpoint sources. These are devices where traffic originates and ends. Endpoint devices take the bulk of network bandwidth. Devices that fall under this category are servers, hosts, IoT devices, printers, virtual machines, cloud resources, mobile phones, tablets. Flows. A network traffic flow is typically determined by the service available on network, such as Active Directory, SMB, HTTPS, and so on. And we can group these into flows into north-south and east-west traffic. North-south is mentioned closely with as it flows from LAN to the WAN and vice versa. Okay. East-west traffic stays within the corporate LAN, so it's often in the local network, so it's often monitored less. Okay. Flow examples. We can see that there is a WAN, so the wide network, so that are the web servers, and this is LAN, so local network, like intermediary, those are those routers, switch, and host is the endpoint. And of course, firewalls that blocks the unwanted DNS requests or any attacks. External DNS. DNS traffic within a corporate network starts when a host sends a DNS query. The host sends the query to the internal DNS server on port 53, which will then act on behalf of the host. First, it will check it has an answer to the query in its cache. If not, it will send the query via the router through the firewall to the configured DNS server. The answer will then follow the same path to the internal DNS server, which will then forward to the host. The network diagram below shows a simplified flow. Okay, and another is SMB with Kerberos. When a host opens a share to, for example, file server marketing, an SMB session is sent up. So server message block as a communication protocol origin developer. That's not important. First, authentication is done via Kerberos. What is that? Kerberos is a computer network authentication protocol that operates based on tickets, allowing nodes to securely prove their identity to one another over a non-secure network. So it's a kind of security program that filters and now the host requests service ticket using the ticket granting ticket received earlier. The host then uses this ticket to establish the SMB connection. Once the SMB session is set up, the host can access the share. Below we see a simplified network diagram of the flow. Oh, there's a lot of here to learn. And it's really interesting information because it's actually show us how the network system works in the larger companies and also in a local network, but in a wide spectrum, in a wide network. And let's just take a look at this graph. So from host, they establish SMB sessions to each server. Domain control SMB server. In the middle is switch. So this is like SMB server and KDC servers are the kind of authentication. So it checks the logging and all this stuff. Okay, so which category of devices generates the most traffic in a network? What do you think? What category of devices generates the most traffic in network? Just think about it. What devices? Maybe switches or routers. Traffic, east-west traffic. Flows. As in the corporate network, we can group these flows into three: south and west. Which one has the most traffic? What category? There are different variations of HTTP's network traffic flows, but which traffic has the most traffic? Let's check web server because this web server doesn't. Which category of devices generates the most traffic in a network? most well-known services in this category are client-server protocols. Stream ingress and egress. Ingress are the inbound traffic and egress are outbound stream. All this traffic passes the firewall in one way or another. Which one it will be? Which category of devices generates the most traffic in a network? Let's find devices. Sources. As mentioned, two traffic sources exist: endpoint and intermediary. Let's check endpoint devices, because those are the phones, tablets, and so on. Endpoint. Yeah, this is the one. So normal devices like phones, tablets, printers, those are the devices that generates the most traffic in a network. Before an SMB, so server message block session, can be established, which service needs to be contacted first for authentication? Before an NCB session can be established, which service needs to be contacted first? Let's find this SMB. A network traffic flow is typically determined by the services available in the network, such as Active Directory, SMB, HTTP, and so on. Typically corporate network. We can group these flows into the traffic. So the question is, before an NCB session can be established, which service needs to be contacted first for authentication? I think it says in here, SMB with Kerberos. When a host opens a share, session is set up. First authentication is done with Kerberos. So the authentication is done with the Kerberos. What does TLS stands for? Transport layer system. Transport layer. TLS. Transport layer security. What is that? Is a cryptographic protocol that secures communications over a network. Okay, so security.